This is Higher Notes 1.6 Special Relativity, Part 3 Muon Problems. Well, in this diagram we can see the Earth's surface, and we've drawn a dotted line up at the top to show the top of the atmosphere. So top of atmosphere. And that's about 100 kilometers up from the Earth's surface, approximately. There isn't a sharp dividing line at the top of the atmosphere, but we're going to assume there is one here. So what the scenario is here is that the atmosphere is constantly bombarded by what are called cosmic rays, and cosmic rays are streams of particles that come from space. They have their origin in stars and in other places. They consist of a whole range of particles, but a very common particle is a proton flying at very high speed. So a cosmic ray proton, we will imagine, comes flying in, and here he is, comes into the atmosphere, and at some point up quite high in the atmosphere, this cosmic ray proton will collide with the nucleus of one of the gases of the atmosphere. The atmosphere, of course, is mainly nitrogen and oxygen. So there's a collision, and when that happens, there's an interaction between the proton and the gas nucleus, and a spray of particles comes off. And one of the particles that comes off is a muon. There's the muon. And a muon is a lepton. It's a light, relatively light particle. It's kind of similar to an electron. It's got a 1 negative charge. It's got spin 1/2, so it's a fermion, and it's a bit heavier than an electron, though. So you can think of it as like a kind of heavy electron. Anyway, muons are created, and they come flying off. Now, typically, muons only last for a fraction of a second. So a typical sort of half-life for a muon is about 2.2 microseconds. So if you have a group of muons, after about 2.2 microseconds, half of them will have changed into some other particle. Now, it turns out that 2.2 microseconds then is not enough time for the muon to reach the Earth. So you would sort of think that the muon would only reach the level shown in the diagram in its 2.2 microseconds. However, muons are in fact detected on Earth. They do indeed reach the Earth's surface. So that muon journey goes all the way from there right down to here. Now, without knowledge of special relativity, that couldn't be explained, because the muon just shouldn't live long enough to be able to cover that distance, even though it's travelling very, very close to the speed of light. So we can only explain this by invoking time dilation. So here we have an example which will hopefully make all of this clear to you. So on Earth, it's known that a muon has a half-life of 2.2 microseconds. So of course what that means is that on average half of any muons produced will have decayed into something else after 2.2 microseconds. So we're going to take that as the length of time the muon's around, essentially, before it changes into something else. Now, typically the muon travels at 99.9653% times the speed of light. So clearly very much a relativistic speed. So we then want to show that time dilation theory is needed to explain how this muon reaches the Earth's surface. Okay. So we're basically going to do a speed distance time calculation in our solution from the perspective of the muon. So we're going to imagine the muon is like a little spaceship and that we are a miniaturized astronaut on the spaceship traveling inside the muon. So we're inside the muon's reference frame. So we're looking at this from the perspective of the muon. So let me just clear something up down here before we go any further. So let's list our variables: speed, distance, and time. Well, as I said, the speed is going to be 99.9653% of c. Very much relativistic speed. Let's work out how far that muon would travel as seen by the muon, given the time that it has to exist. And that time, of course, is the 2.2 microseconds, which I'll put in scientific notation there. Now, if you think back to your previous work, when a spaceship is traveling, say, between the Earth and a star, Proxima Centauri, for example, and it looks at the distance it's traveling, one of the techniques we use is we imagine a big measuring tape stretched out between the Earth and that star. And as the astronaut in the spaceship looks at the measuring tape, he sees the contracted length. He measures proper time, but he sees the contracted length that he's travelled. So this muon is going to see the contracted length. So I'm going to call that d dash. Okay. So let's look at what length the muon thinks it has travelled, so to speak. Well, we can simply say that distance equals speed times time. And this is my d dash, it's my contracted length, remember. So it's 99.9653 divided by 100 to make a percentage, times 3 times 10 to the 8 meters per second. So that's my v. Multiplying that by my time as measured by the muon, 2.2 times 10 to the minus 6. Now when you do that, then the contracted length d dash that the muon thinks it's travelled is 660 meters. So that is the contracted length seen by the muon. Now, the thing is, if we go back to our diagram, that 660 meters is probably only going to take the muon to maybe about there, right? I mean, I'm kind of exaggerating that in this diagram, to be honest. Okay, it's nowhere near the Earth's surface, that's the key thing. So the problem then is, if that's what the muon thinks it's travelled, what's going on? Well, the fact is the muon has in fact travelled a longer distance from A to B, the uncontracted length, if you like, and this would be the length that would be measured by an observer on the Earth, who's stationary, if you like, with respect to the muon. So How can we explain that? Well, let's do a calculation on the time. Let's look at the time. The muon thinks it's been travelling for 2.2 times 10 to the minus 6 seconds. So let's apply our time dilation equation. T dash equals 1 over square root of 1 minus v squared over c squared times t. Now, t dash, of course, is the dilated time. And t is what we often refer to as the proper time, and that's the one seen by the muon. This dilated time, of course, is seen by an Earth observer. So if you imagine back to our example in class of the twins, where the one twin goes off on the spaceship and travels at relativistic speeds, it's the guy who stays on Earth, the one who gets much older, who measures the dilated time, t dash, the stretched out time if you like, whereas the twin who comes back younger measures the proper time, t. So in this case, the Earth observer is like the old twin, so to speak, and the muon is like the spaceship of the travelling astronaut twin. Right, anyway, when we put in our numbers, we get 1 over square root. Now remember, if you know the percentage, then you can just put it in as a decimal, so that becomes 1 minus 0.9999653 all squared. Okay, because 99.9653% is exactly the same thing as 0.999653. So that's all squared. And of course we've got to multiply that by the t, the proper time t, so that's the 2.2 times 10 to the minus 6 seconds. Well, when you work out the t dash then, the dilated time, you get 84 microseconds. Now the muon thinks that it's only got 2.2 microseconds. That's what it measures its time of flight as, but the Earth observer measures it to be 84 microseconds, a considerably longer period of time. So if we now do a speed distance time calculation, but this time from the perspective, i.e. reference frame, of the Earth observer, so we have our speed distance time calculation again, and we're interested in the distance that's actually travelled. That's what we're looking for. We know the relative speed is the speed that we've got up here, that 99.99 times percent of c, right? So let's just get that 99.9653. So that's 99.9653% of 3 times 10 to the 8. And from the Earth observer's perspective, remember, he measures t dash, the longer dilated time. So we now apply that time to the muon. Now obviously from the Earth observer's perspective, the muon has much more time to reach the Earth. Well, let's see if the distance travelled matches what we would expect. So when we do a distance is speed times time calculation now, we'll get that 99.9653 over 100 times 3 times 10 to the 8. And we're multiplying that by the dilated time, so that's 84 times 10 to the minus 6. And when you work the distance that the Earth observer sees the muon travelling, you get 2.52 times 10 to the 4 meters. So, from the point of view of the Earth observer then, the muon actually travels, what's that, about 25.2 kilometers. And if we go back to our diagram, then that 25.2 kilometers is that distance there that the muon has travelled. So as far as the Earth observer is concerned, then the muon can indeed travel that long distance from the top of the atmosphere down to the Earth. And these muon problems are quite common in the exam papers, so please make sure that you can work with them and solve them confidently. And that brings us to the end of the relativity note part 3.